So welcome everyone to the day 2 of inaugural tinyML Asia Technical Forum. I'm Sakya Dasgupta, CEO and founder of Edge Cortex, and I'll be chairing today's session. It's a great pleasure to talking to all of you from Tokyo here. It's my pleasure to introduce Professor Kai Yu from the Shanghai Jiao University, and he's going to talk to us today about highly efficient neural network language model compression. Professor Kai is at the Computer Science and Engineering Department and the director of the Speech and Language Processing Center AI Institute of Shanghai Jiao University. He earned his BS and MS degrees from the Tsinghua University and a PhD from the Cambridge University. He also serves as the director of the Academic and IP Committee of China AI Industry Alliance and is also the associate director of the Technical Committee of China Alliance of Intelligent Speech Technology Industry. He also founded the AI Speech Company to commercialize state-of-the-art speech and language processing technology. So it's a pleasure to have him give this session talk for us. Professor Kai, over to you.
Thank you for the kind introduction. It's my pleasure to give this talk to introduce our recent work on language model compression. Okay, so we all know that deep learning on edge devices are quite important. Usually we care about two things. One is computation complexity, another is parameter size. Actually, many researchers have been talking about computation complexity a lot, but today my focus is on reducing the parameter size, i.e. the memory side. So you can see on the left side, there's a figure about a neural network on embedded devices. Usually for our neural network, language model neural network, we have about 400 megabytes, but we need to compress it down to almost like 3 megabytes also in our embedded devices. So before, people have been talking about image a lot. So let's see the difference between a neural network for like image processing or video processing compared to neural network for natural language processing. On the left, we can see the image recognition, a typical neural network for image recognition. The input layer is actually the kernel size for each convolution kernel. It's around, say, if we have a 11 by 11 kernel with 3 channels, the input parameter size for this particular neural network is only about 34K. But in comparison, if we are talking about language model, we are talking about natural language processing, the input layer is much larger. In a typical case, if we have just, let's say, 7K vocabulary, which is not a big vocabulary, with, for example, 400-dimensional vector as the word embedding, the parameter we have is almost 3 million. That's a lot bigger than the image recognition. Previously, almost all efforts are put on compressing the neural network structure, but ignoring the input side. And today, I'm going to focus on the input side. So let's look at the existing compression methods for the language model. So what is a language model? Basically, I need to explain that. A language model is a probabilistic model of a language which gives a probability of the whole word sequence. As you can see, it's basically given the word sequence, we need to calculate the probability. A simple way to do this is the so-called n-gram model. It is just a word piece. It's a contiguous sequence of n tokens from a given piece of text. Say, when we predict the probability of the whole word sequence, we just predict the probability of each word given a fixed size history. This is how we do that under the n-gram framework. How do we evaluate the performance of a language model? Since the language model is a prediction model, we basically use prediction error to evaluate this model. The prediction error of a language model is defined as just a normalized entropy. It's basically, we call it perplexity. It looks like an error. We don't need to go into detail on this, but you just remember later we will use this measure to evaluate how a language model is good or not. Since language model is a very fundamental, very fundamental tool for natural language processing, we can use that for almost all tasks like spelling checking, speech recognition, machine translation, and so on. So let's look at the memory the language model uses. Taking the traditional n-gram language model as an example. So the so-called n-gram is basically an enumeration of all possible combinations of word pieces. So we need to predict a word given a fixed size history. So if we don't have any history, we have the so-called unigram model. It's basically the probability of each word. And if we have a bigram history, which means we have only one word as the history and predict the next word, we have the so-called bigram model. Typically, in a speech recognition task, well, very complicated speech recognition task, when we do the speech recognition rescoring, we can use up to 5. Well, usually we use 4, but we can use up to 5. If we use up to 5 n-gram language model, what we can see is with a large vocabulary of 120K and with a perplexity of around 300, the size of the whole language model is 45 gig. This is actually being used in commercial system, in a cloud system. That's this size of n-gram model actually prohibits the whole large vocabulary continuous speech recognition being used on an embedded device. We can only use that in the cloud. What if we use neural network? If we use a neural network language model, it's no longer a counting-based model. It's something like a parametric model. So given all the input history words, we use a parametric model to predict the prediction, to predict the probability of the next word. With this neural network language model, the size is significantly reduced to 400 megabytes with even improved perplexity to 210. So remember, the previous one is 300, and now we have 210. So it gets very big reduction, and the size is also greatly reduced. However, 400 megabytes is still too big to be used in embedded devices. But what caused this problem is actually the so-called word embedding. So when we do the prediction, one thing we cannot ignore is we have to have a vector for each possible word. That means for each for a vocabulary of 120K, we need to have 120K vectors. Each vector is a distributed representation of a word, which means it's a vector with real value. So like here, we project each word into the continuous vector space as a vector so that we can compare or even do calculation between words, as you can see here. But for the in a normal case, the embedding dimension is around like 200 to 1000. So we would have a 100K times about 200 matrix. And this is very big. If you see the size of a neural network language model, over 90% of the neural network language model is being used by the word embeddings. And only less than 10% is about the real neural network parameters. As you can see from this table, we have the in a wiki text corpus, if we have 26K words, the embedding size is almost 1 gig. And if we use LSTM language model, the neural network size is only 100 megabytes. So the real problem lies in the word embedding. But how do we do the compression? There are two ways to do neural network compressions. One is to change the structure. Another is to do quantization. For the structure approach, people usually can design new structure, like use GRU to replace LSTM, or use some kind of general approaches to do some structured factorization, like SVD or doing pruning. We shall talk about this a little bit. Another a direction is to do quantization. When we do structured design, we usually focus on general approaches, since very specific structured design is sort of highly complicated and cannot be applicable to different models. So today I'm going to talk about only on the general approaches. So the one typical general approach is singular value decomposition. As you can see from here, for singular value decomposition, we just factorize a matrix to like three different matrices, and we use the rank approximation to reduce the rank in the middle so that we can reduce the total number of parameters. With different rank approximation K, we have different compression ratio. One example here is if on ImageNet, we use SVD to get about 13.4 reduction in weights, we will have about 0.84 increase in error. We can only get almost no loss in error if we keep our reduction in weights to say like about three times compression. So this method is very ineffective. How about pruning? Pruning is another method. We just need to get rid of all the null nodes from neural network. We have done some interesting pruning work, automatic pruning, by just calculating the absolute value of each weight to design a so-called importance function, which is the absolute value of all outgoing weights or all incoming weights, and then we do a average. So we call it importance function. By using importance function, if we only have we have no incoming weights or we have no outgoing weights, we can just reduce this node. Using important function to do node pruning, we can automatically prune a deep neural network into this shape. So in the middle, the nodes are pruned heavily, and at the beginning for feature extraction, and in the end for doing classification, the nodes are retained more. From this figure, we can see if we do node pruning, we can almost get half of the size reduced without degradation on word error rate, basically means speech recognition error. So it's about half. That is the compression ratio, it's about 2. Those are not very efficient. Actually, for embedded devices, the most efficient ways are always quantization based, or at least you have to use quantization combined with other approaches. So let's see the quantization based approaches. One very naive method is to do scalar quantization. Basically, we just convert, in this example, we convert 32-bit float into a 2-bit integer. So we can get the compression ratio of 32 divided by k. This k here is 2. For vector quantization, we need to construct a code book for the whole space, and then we use an indexed for each row in this matrix. Here, we have a code book of 2, and we can use 1 bit to represent the whole matrix. So the quantization compression ratio is quite big. When we do scalar quantization, we need to do fixed point quantization training. Here, if we do vector quantization, we can reduce the parameter even more than normal fixed point quantization. So how do we do fixed point quantization during training? Well, we can either do the quantization directly on neural network, or we can do the quantization and then we do some retraining to refine the performance. Here is one example of doing fixed point quantization. In this example, for the full precision weight, we first do normalization, and then we chunk the region to 3 parts. For the middle part, just use 0. For the left and right part, we can use fixed point to represent. So this is a quantization to like 0, -1, and 1. But during training, we can train the basis, basically the lower bound and upper bound, to real values, so that we can have a codebook-like thing to map each quantized bit. By using this, this kind of three bit ternary weight method is getting improved performance compared to a 1 bit or 2 bit method. But this is still not quite efficient. What we try to propose is we don't just want to do scalar quantization or simple naive vector quantization. What we try to do is to make use some structure inside the word embedding matrix to do the so-called product quantization. So here is the solution. We want to compress word representation via the so-called product quantization. Let's compare the normal vector quantization to the product quantization. For the original word embedding matrix, we have a e-dimensional vector for each word, and we have the vocabulary of, for example, 120K number of words. That's the original matrix. If we do vector quantization, we basically need to design a codebook. Let's say we have C different clusters. And then for each word, we just select the index from the codebook so that we can use an integer, a index of the codebook to represent each word. In this case, the whole parameters for the quantized word matrix is the C clusters in the codebook and the index for each word. But this is not efficient. What we think is more efficient is we do the so-called product quantization. We sort of need to split the embedding dimension into 2 groups. For example, into multiple groups, for example, 2 or maybe 3 to 4. This is a subspace partition. For each subspace here, we design a specific codebook. And then we can use index in this subspace to represent each word in this subspace. Similarly, we can do that for the rest. In this case, we have a codebook for each subspace and an index for each subspace. With the combinatory effect, this is a lot more effective. So this figure shows, given the fixed memory size of embedding layer, how many possible words we can represent. In this case, you can see for the naive vector quantization, the increase of possible words, this is the blue curve. The increase of the possible words we can represent given the memory size is very small. But if we do product quantization, especially when we partition the whole space into more subspaces, the representation power is exponentially increased. For example, in this red curve where we have 6 partitions, given 1,000 memory size, we can have almost 10 to the power of 15 number of words. So that would cover all possible words. While in contrast, for the vector quantization, we can only have, for example, 1,000 words. That's a lot different. This is another comparison from different angle with different. So in the left figure, with a fixed group size, for example, 4. If we have 100 codebook entries, we can almost represent all possible words without losing any degradation, without losing any performance, because the y-axis is the perplexity. Basically, it's the prediction error. So basically, with 4, it's almost like 8 or maybe more. So 4 is enough if we have 1,000 code books. So we can see from this, with normal vector quantization, the performance degradation is a lot. Say in the left figure, you can see with 4 different groups, the degradation is a lot. And this product quantization also gives us some hints on how to group words. Before, if we use only vector quantization, we can only group vector together. So different words would have different similarity, but we can not thoroughly analyze this similarity. But if we split it into subspaces, you can see here for the word gray, in the subspace 1, it's related to colored, orange. But for subspace 2, it's related to haired, tabby, and so on. For subspace 3, it's related to brown and pink. So basically, from different angle, we can sort of analyze each word. This is a side product. Okay, now let's look at the speech recognition performance. So with language model, we can do speech recognition. If we use structured quantization, we can get like 12 times of compression ratio with very little performance degradation. In this case, you can see this blue guy is the baseline, and the orange guy is our product quantization. The memory reduced about 12, and our perplexity, this is the pure language model performance, only increased a little bit, and the word error rate rescoring 10.3 versus 10.4, or almost no change. And we can combine the product quantization with even more quantization method like binarization. So let's first talk about binarization a little bit. For binarization, basically it means we want to use binarized parameter matrix. But to recover the performance, we don't want to use binarized parameter for every single parameter. We only use that for parameter matrix, but we also introduce some scaling float vector to recover the performance. So our bias, and when we calculate the activation, we all use the fixed point 32 real value. When we train the binarized parameter matrix, basically in the forward propagation, we quantize all the parameters so that we only have -1 and +1. And when we do back propagation, we sort of regard it as a real value. We do normal back propagation. So this is how we train binarized neural network. And here we can do binarization on embedding matrix. So before, for each word, we use a distributed vector for the word. That is a real valued vector. And now we just use a binarized vector and use the training method I just mentioned before. So this is the first step. We can do soft binarization for the embedding matrix. this by doing this, we already get a theoretical compression ratio of 32. How do we do the training? I probably wouldn't go into details, but the basic method is just to use data to refine that, but not just with the raw data. We also need to have a full precision model. We propagate the input through full precision model, get the prediction distribution, and we use the prediction distribution plus the data label as the supervision signal to do backpropagation to refine our binarized model so that the performance will be improved. So this is the performance of binarization on both embedding layers and hidden LSTM layers for language model training. The left figure is the memory size comparison from the real number 100, almost 200 megabyte reduced down to 6.6 megabyte. And if you see the perplexity, that is the language model prediction error, if we just do hard binarization, we get big degradation, the error increase. But if we do soft binarization, basically use the so-called knowledge distillation method to retrain the model, we can get even improved performance. Similar for the word error rate, the speech recognition case. So now we have two methods. One is to do product quantization to split the embedding space into subspace. Another is to do binarized quantization to reduce the memory from the real value space to a binary space. How about combine the two? So this is what we do to combine the two. Let's see from the left. So the left is the baseline. The input is the original word embedding matrix, one vector per word. If we do product quantization, basically we have a structured word word embedding representation. The whole space is split into, in this case, in this example, two subspaces. We have two small vectors to form the codebook, and we have the index combining together to form the whole embedding, the whole embedding space. And this is the binarization. From the baseline to the binarization is just to binarize the word embedding matrix. And if we combine PQ and binarization together, we have, for each word, we have split subspace, and each subspace is no longer a real valued space, it's a binary space. And we have the index to represent each word. So this is how we get our binarized and product quantized space. So let's see the final result. When combining the two, if we see the memory size reduction, it reduced down from 200 megabyte to just 1.5 megabyte. So we get over 100 compression ratio. And if we see the prediction error, for language model prediction error from 89.1 to 89.2, almost no change. For the speech recognition error from 10.3 to 10.3, no change at all. So by conclusion, neural network language model compression is really a key problem of the putting natural language processing tasks into into embedded devices. And the large vocabulary and word embedding layers are really the core challenges. And we can use product quantization and the binarization combining together. We can use the two techniques to achieve over 100 times compression ratio on neural network language model without performance degradation. Okay, thank you. I'm happy to take a few questions.
Thanks, Kai, for that lovely presentation and introduction to compression of language models. I think we have time for just one question. There's a question from Rafiul Shamir. He says that if we are optimizing the models for size, in this case with quantization, do we lose some information from the original signal or the ability to detect secondary attributes like tone of voice, pitch, etc.?
Well, first, today I'm talking about the language model. It has nothing to do with pitch and so on. That's about the feature extraction for speech recognition. That's the first answer. But secondly, actually we don't lose, I don't think we lose information because we are using structured method to review the hidden and real structure of the language. We don't use naive unstructured method. So we don't lose information. We just restructure it and we use a better way to represent it. This is the key of product quantization. But for binarization, it definitely loses some information. Yeah.
Excellent. Thanks a lot, Kai, once again. I would like to thank our sponsors once again, without whom the tinyML Asia Forum would not be possible and be available for free of charge. Starting with ARM, our premier sponsor, the Software and Hardware Foundation for tinyML. Edge Cortex, their dynamic neural accelerator brings near cloud performance to the edge devices. Finally, SynSense. SynSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. Thanks a lot once again to all our sponsors. I would also like to thank our partners, conference partner SHAI, as well as all our media partners. So that brings us to the end of today's session, and I look forward to seeing all of you once again tomorrow for the day 3 of tinyML Asia. Thank you, everyone. Thanks all our speakers and all our sponsors once again. Thank you.